Hey, welcome to the Explainer. Today we're going to get into something really cool. How do we actually teach a machine to know things? We're talking about building an AI's mind, right from the very beginning.
So let's just jump right in. How does an AI actually know anything? I mean, it's not magic, right? And it's way more than just lines and lines of code. What we're really doing is building a kind of mind for the machine. We have to give it a language, a special language, so it can understand the world. Okay, so the very first step in this whole journey, starting from total scratch, is to build a language. But not just any language. It has to be super powerful, totally formal, and this is the key part, have absolutely zero room for confusion. Not like our messy human languages. This system has a fancy name, First-Order Predicate Calculus, or FOPC for short. You can also just call it first-order logic. And you can think of it as like the official grammar for an AI's thoughts. It's this rock-solid foundation where every single statement means exactly one thing, no wiggle room. And this slide, this is a perfect example of what I'm talking about. On the left, you've got a simple English sentence we can all get behind. All humans are mortal. Easy. But look at the right. That's what the machine sees. It's a logical statement with zero ambiguity. It literally reads, for all things X, if X is a human, then it follows that X is mortal. See? No room for interpretation. So, these are the fundamental building blocks, kind of like the Lego bricks of machine logic. You've got predicates for properties, constants for specific things like Socrates, and quantifiers to make these big general statements. With just these few pieces, FOPC can describe really complex rules and relationships about, well, pretty much anything. Okay, so here's the catch. While FOPC is incredibly powerful, it's also really, really slow. Think of it like using a massive supercomputer just to do simple addition. It's overkill, and it gets bogged down. For the kind of split-second decisions you need in the real world, it's just not practical. And that limitation, well, it led to the next big idea.
All right, a new section. To make logic faster, to make it actually work in the real world, the early AI pioneers came up with a much simpler, more direct system. They basically created an engine for practical logic, all based on simple rules.
And these are called production rules. The best way to think about them is like simple recipes for thinking. If this happens, then do that. If you see these conditions, then you can make this conclusion. It's super direct, it's actionable, and this idea became the core of what we now call expert systems.
And this is how that engine actually works. It's a constant three-step cycle. First, it matches the facts it knows against all the rules it has. Then, it selects the best rule to use, if a few of them fit. And finally, it executes that rule, which usually adds a new fact to its memory. And it just does this, over and over and over, chaining little pieces of knowledge together until it reaches some kind of conclusion. Now, it turns out there are two main ways to run that engine. You can either start with the facts you have and just apply rules to see where you end up. That's called forward chaining. It's great for things like diagnosis. Or you can start with a goal, a hypothesis you want to prove, and work backward to find the facts that support it. And you guessed it, that's called backward chaining.
But let's be real, our brains don't just work with a big list of if-then rules, right? Our knowledge it's a messy web of interconnected ideas. So the next big challenge for AI researchers was, how do we get a machine to represent that web? The answer was something called a semantic net. And this was a huge shift in thinking. We're moving away from rigid step-by-step rules to something that looks a lot more like a map of knowledge. You have nodes, which are the concepts, and then you have links between them, which are the relationships. It's actually a lot like how our own brains seem to connect ideas. And here's a super simple example. The network knows that a cat is a type of animal. It also knows that an animal has skin. So because of that is a link, the AI can automatically infer that a cat must also have skin. It inherits that property. This whole idea of inheritance is what makes these knowledge webs so incredibly powerful. Okay, next section. Semantic nets were a huge leap forward, for sure, but they kind of struggled with context, with common sense situations. Like, think about going to a restaurant. How do you represent all the stuff that usually happens? It's not just a list of things like table and food, it's a whole sequence of events, right?
Well, the legendary AI pioneer Marvin Minsky came up with a solution called frames. And the whole idea was to package knowledge into these, blueprints, templates for common, stereotyped situations. It's a lot like how you and I have a mental script for what to do in a restaurant, a library, or an airport.
Take a look at this. This is a frame for a restaurant visit. It has slots for things like the different roles, customer, waiter, and fillers that describe the sequence of scenes. You enter, you order, you eat, you pay, you leave. Now here's the cool part. If you tell the AI that someone paid the bill, it can use this frame to guess, to infer that they must have already ordered and eaten. That's common sense, but for a machine.
But of course, this opened up a whole new can of worms, a really tricky one. How do you get an AI to understand something like a belief? Look at that sentence. John believes that Mary loves rum. How do you represent that without just making Mary loves rum a universal fact in the system? You need a way to separate belief from reality.
The solution they came up with was brilliant: partitioned semantic nets. The idea is to basically build virtual walls inside the knowledge web. You group information into different partitions or contexts, so the AI can understand that what John believes is in one box and what is actually true is in a totally different box. This was a huge, huge leap for getting machines to understand the nuances of language. All right, so we've gone on this whole journey, right? From super rigid, pure logic, all the way to these complex blueprints for situations. And you might be sitting there thinking, okay, that's interesting history, but why does any of this old school stuff matter for the AI I'm using on my phone right now?
Well, it matters a lot because these foundational ideas are the invisible skeleton inside so many of today's AI systems. Those simple if-then production rules, they're still running things like medical diagnosis systems and factory controls. And those semantic nets and frames we talked about, they are the direct ancestors of the huge knowledge graphs that power things like Google's search engine and help chatbots actually understand the context of what you're saying.
And this quote here really just nails the whole point of this journey. It says, with old school programming, you have to tell the computer how to solve a problem, step by step. But with this kind of logic-based AI, you just describe what is true about the world, and you let the system figure out for itself how to get to the answer. It's a totally different way of thinking. And that really brings us to the big final question, the one I want to leave you with. We've gotten really good at building these incredible, complex structures to represent knowledge inside a computer. But is representing knowledge the same thing as understanding it? And that right there is the question that AI researchers are still wrestling with today as they build on these amazing foundations.